I've checked everything you sent. I've grouped, arranged the materials, and I'm gonna first start from some general basic principles important for taking any course, not just geometry, because what I see in your work is you don't have issues with conceptual understanding. I don't think that's a problem, but I can see you made a couple of mistakes here and there, and the reason is, again, not conceptual misunderstanding, but as many other students I've seen, you make one important mistake. You're trying to do as much work as possible in your mind. On the exam, that's understandable, because on the exam, you want to save time. So writing takes time and you want to avoid that. But when you solve problems at home, you should, well, first of all, you should use more paper, not trying to cramp everything in one page and trying to show all the steps. And in order to get a habit of making a transition from pure knowledge, from conceptual knowledge, to a problem solution, it's very important to practice in explaining, maybe just to yourself, every step you make, and for every step you make, you should be able to say, to establish a reason why do you make this step. And we'll go back to your specific examples later. First, another general and very important principle in any scientific field, geometry, trigonometry, algebra, physics, chemistry, biology, geology. The foundation is based on things which do not require understanding. This is a common misconception. So when a book or a teacher is asking you, can you understand that? General answer, well, to a teacher, of course, is yes, I can. But to yourself, well, sometimes I don't have to, because there are things which have been developing for hundreds, sometimes thousands of years, and we just need to know those things. Those things have to be a part of our memory or dictionary, like a theorem, Pythagorean theorem, or another theorem, doesn't really matter. These things at first require just pure memorizing. Of course, you have to be able to read it and say out loud. And when you say, you of course need to understand the meaning of the words in that sentence. But this is one thing. How to apply that sentence, that theorem, to a specific problem, it's a different practice. And that's where certain amount of understanding will be required. But initially, everything is based on just memorizing names of things. In science, we call it definitions, and rules. Rules, well, in geometry, rules have different names. Axiom, postulate, theorem. in physics, chemistry, that could have been a law, but those are rules. So names and rules, those things should be a part of memory. That's it. And of course, your textbook has all the rules. Well, I don't have the access to your textbook, but there are many similar textbooks available online. So this is just an example. You don't have to read it. It's just an example. A set of rules which every student who studies this topic, this material, needs to memorize. But memorization, of course, takes time. It's like learning a foreign language. I don't know if you learn a foreign language, I don't know, but it's very similar. You just open the dictionary and study, okay. Arm, рука in Russian, or I don't know, in Spanish or in the Chinese or in any other language. These connections between a word you know and a word which represents the same meaning in different situation. That's what we call a dictionary, those connections. And every textbook has those connections. So for example, you need to know what is a proportion or a mean, exterior, or what is a triangle, a line, this is something you should do on your own. And while doing that, the best way is making your own dictionary. Take a notebook or some paper clips. And if you see in a textbook a definition, usually it's like a blue box or something, make a copy. It's important that you would make a copy by your own hand, because in addition to just reading, which excites a certain number of neurons in your mind, you also will be acting with your muscles. And if you read out loud, that will enact another set of muscles. And all those actions, they ignite inside additional neurons in your brain. And learning is making connections in the brain. That's what it is. Learning of anything. How to drive, how to swim, how to do geometry. It's just about what is happening in our brain. We need to help our brain to be active and to make as many connections as possible. Plus, in the future, it will save time for you. If you're solving a problem, like this one right here, you need to say what angles are congruent, what angles are supplementary. This problem does not require understanding of geometry. This problem requires understanding of, well, English language and being able to match pictures and names. Basically, that's it. If you don't know these names, exterior, interior, congruent, supplementary, you will not be able to answer questions about this problem. So this requires just pure, straightforward memorizing. How would these two angles be named? Yeah. Check. And if you don't remember, and of course, naturally, it takes time to memorize all the things. You could go quickly back to the notes, to your own dictionary, find this very page, read it, and make the match. And you would answer, okay, for example, 7 and 3, congruent, yeah, etc., etc. So this is an example of a situation. Oh, I see. Now you're supposed to be able to see what I see. Yeah, I don't like, I'm not sure why. Oh, maybe because you're screen has a different ratio. That is why, so mine is wider.
I can move your camera like somewhere else. I can like see the thing better.
That's fine. I've got what I'm saying right now is just an illustration of general principles. I am sure you have no problem with answering these questions, but it's very important to choose a simple situation to illustrate a general principle. And the general principle is you need to learn the language. And number one thing is to have all this information handy at your hand, so you could find it quickly. And number two, ideally, to put all this information in your memory. I am not sure if in your class you need to know how to prove a theorem. You've got a problem that is based on this theorem, so you need to know how it works. But I don't think you need to know how to prove it. However, I would strongly suggest if you see a theorem in a textbook, find the proof. You don't have to invent it on your own. No, that's a completely different exercise. But you can easily find it, just like I did in a textbook or do this Google search or whatever, and then follow this proof. And for each step, step one, step two, you should ask yourself, okay, do I see why this step was used? And if the answer is yes, I do, perfect, move to the next step. If you are not sure, well, at least you can make a question mark and then we can discuss it later, or you can discuss it to anybody else, teacher, your friend. But it's very important to understand the reason for each step you're making. Well, please feel free to stop me and ask any question anytime you feel like you want to, okay? So this is an illustration of a general approach to solving a problem. These are simple problems. You've done these problems. What I can tell you again, you did a lot of work in your mind. Again, on the exam, that would be fine to save time. But if this would have been a homework, I would suggest take an extra piece of paper and use that extra piece to write every step of the reasoning. For example, the hint tells you use the Pythagorean theorem or blah, blah, blah. Okay, of course, this is not about using Pythagorean theorem. Why? Because none of these triangles is the right triangle. But what do you need to use? Well, you need to know. This is just a name, triangle sum theorem. Okay, it's like my name is Mr. Rick. But you need to know what does this theorem mean? Can you tell me the triangle sum theory what it means? Yes, because it's right here on the screen. Well, without a screen, without this hint, you should have been able to say it out loud. That's one thing, say it. But there's another thing, you need to be able to write it in a general form. In a general form, if you've got any triangle with three angles, how do you write mathematically this theorem? Can you tell me?
A plus C equals 180.
Well, you get a triangle. Triangle has three angles. So A plus B plus C equals 180. This is the theorem expressed mathematically. If you write it like a plus c equals 180 or a plus b equals 90, this is going to be wrong. So, and this is just a knowledge, but this knowledge you should be able to apply to any triangle. And if you, let's say, try to apply this knowledge to a triangle number 15, first of all, the theorem uses symbols A, B, C. You don't have those symbols. So if you want to use a theorem, strictly speaking, your first step is making a triangle, your specific triangle, look like a general triangle for the theorem. Now, you can apply a theorem and you can write, okay, for, I don't know, you know how to solve it, but it's not about solving a problem. It's about applying a strategy. Because if you get a habit of using this strategy for solving simple problems in the future, you will be able to apply the same strategy for solving problems, more complicated problems, which you will not be able to do in your mind. So you will have to force yourself into applying strategy anyway. So it's better to practice now. So you said it, you wrote it. That was step number 3. And now step number 4, you're applying. This is A, this is B, but what do you write for C? There is nothing here. So you write just C, there is no other option for you, and this is equal to 180. And this is your straightforward application of a theorem, but it doesn't give you the answer just yet. So using this theorem is not enough. And this is a very common situation when we have to solve a problem. We make several steps and we kind of ran into a wall. We need to do something extra. And I know what you did. But again, for every action you make, for every step you make, you have to have a reason. So there is step number 1, step number 2, step number 3, step number 4, step number 5. It requires to connect these two entities. We can see, our brain can recognize that this angle C is supposed to be related to this number 72. How? Well, that's another question. If I write C equals 72, is it a right or wrong statement, mathematical statement?
Wrong.
Wrong, of course. But some people wrote it, and if you say it wrong and you know how to write it in the correct way, you need to know why. So, and the answer to question why is another rule, or in this situation in geometry, another theorem. So now you have to say that another theorem, and you have to write that theorem mathematically, and that theorem says that if you've got a straight angle, and I'll call it alpha beta, the sum will be equal to 180 degrees. That's another theorem. And now we can say C plus 72 equals 180, etc., etc. And the solution will give you the answer, of course. But again, solving a specific problem is not as important as being able to establish all steps one by one that will lead you to the answer. So this is the most important practice in geometry or any science, establishing strategy, steps. And again, for every step, you need to know the exact reason why you can make it. Otherwise, in the future, when problems will be slightly more complicated, you will be making mistakes. Okay, another example. I believe this, actually, I don't know. I don't see any work here, but I would expect, based on work I saw, you get a general idea how to approach these problems. So what would you do? Can you tell me?
I haven't learned it yet, though.
Oh, you haven't?
Yeah, our teacher is gone. She hasn't really teach us any of this stuff, but sign off.
Perfect. So now I understand. So this is the material which was not covered for you. Okay, perfect. So now we can talk about it. So, oops. All right. Probably I'm gonna add an extra page first. But everything I said before is not new to you, right? Good. Well, probably you know some basic postulates that if you got 2 points, you can draw one and only one straight line through these 2 points. And if you got 2 lines, you will have 2 options. Those lines either parallel or they cross. And if they cross, there's only one crossing point. And if you've got 2 lines drawn, and there's a transversal line perpendicular to both, these lines are parallel. So those are things which should be just a part of a kind of handbook. And what happened next? Let's say we've got 2 lines crossing at a certain point, and we've got 2 transversals, meaning 2 other lines crossing. So we can take a ruler, and I suggest, if you study geometry, you need to have handy all these things with you: a ruler, protractor, an angle, compass, and of course a calculator. So we can use a ruler and we can measure length of many different segments. And right here in this picture, you can see triangles. For example, I can call it A, B, C, and I can call it A, let's say D, E, triangles. In this case, based on axioms and principles of Euclidean geometry, and I believe, again, you don't need to know the proof, we can establish just by measuring things that the ratio AB over BD, meaning, well, I can call it also like little a and little b, this ratio A over B will be equal to the ratio on another side of these triangles. I can call it X, I can call it Y, and this will be equal to X over y, or if we use a standard symbol is AC over CE. So this statement is a theorem, and this statement has an actual name. For some reason, when it is adding a page, it is adding a page to the very end. All right. So this is the theorem which I just said out loud. I just stated. And this is the proof of this theorem. I found it on the internet. There are many links. One of these on the screen. So what does it tell us? It tells us that as soon as we see something like this, we should recognize this theorem and we should be able to apply it. That's it. So the first action always is recognition. When we need to solve a new problem, our first intention is trying to remember, have we seen something like that in the past? And if we haven't, we're done, because we don't invent things when we study something. We have to learn things, which means we have to find those things established for us, put it in the memory, and then apply. So this ratio says exactly what I said. The length of this side divided by the length of this side will be equal to the length of this side divided by the length of this side. It's a very old theorem. So now I have to go back to my page, scroll through all this stuff. But again, I prefer using lowercase letters. Let's say you've got something like this. It's exactly the same situation because we just flipped. We could imagine that we'll look at this differently. And I can say, I can call this side A, this side B, this side X, this side Y, and still A over B will be equal to X over Y. And we have to remember that the order matters. X and Y should be opposite to each, X and A should be across opposite to each other. B and Y should be again across. In that case, this is the correct proportion. However, if I would write A over B equals Y over X, I would make a mistake. That would have been wrong. That's it. So this is a new knowledge. That's it. As soon as we see this kind of structure in our memory, should kind of pop up this picture and this proportion. And in mathematics, I've seen you've done proportions before. So if you have a proportion A over B equals X over I, it means many other things. For example, this symbol means hence. It means B over A equals Y over X. Basically, it means we can take a proportion, flip it, but we also can simplify it by getting rid of fraction bars. We don't like fractions, they are complicated. So we can say A times Y equals B times X. So these are extremes. The product of extremes is equal to the product of means. So I don't know if you've heard that terminology, but if you haven't, you have to put it on your dictionary page. These are called extremes of a proportion. These called means of the proportion. And you need to be able to say this statement out loud. It's very important to be able to say in a sentence, in a verbal sentence, every mathematical sentence you might want to use. So now we've learned that. Next question is, how do we apply it? We're here. Well, we'll look at the picture. Well, here it says, use the diagram to prove. Prove means basically we have to do this. But to do that, again, do not try to invent it. It's a standard, well-established, very well-known rule, theorem. Google it, find it, and follow the rules. You need to understand the rules, not invent. And now, next situation, let's say here, apply. Well, there's something very, very wrong with all these pictures. These pictures are too small. A good picture is a large picture. If you do homework and you use a standard like A4 sheet, a good picture should have at least a quarter of it. So the first thing is to redraw a picture, but you don't have to draw the whole picture. You see, this theorem is about triangles. So you can just choose a triangle, choose, it's your choice, and redraw that triangle. For example, you can make a triangle A, B, C like this, and redraw it. A, B, C, a bigger picture, A, B, C. Now we draw the lines, we have to make a copy. Where else? Well, now this line, I can call it, well, actually, if I use a theorem, it helps to use exactly same symbolism. So I want to change my letters. I want to call this A, I want to call this B, this is C, I want to call this D, and I want to call this E. In that case, my specific picture becomes identical to a general picture from a textbook about the theorem. Now, my symbols, Y, and here, I believe it's 9 feet, 10, and here I believe it's Z, Y, 9. All right. So after this first action, now I can apply a theorem. What does the theorem say? Theorem says if I've got this picture, hence I can write this ratio. Now I've got this picture, hence I can write this ratio. So ratio has what? Two parts connected by the equality symbol. So I can write equals. Each part has a fraction bar. And my most important part of reasoning now is just writing numerators, denominators correctly. So maybe you could tell me for this triangle, what ratio should I write based on the theorem we just have learned?
dA over B equals EC.
Yeah, let's try to use symbols that represents the length of each side. You know, just a single symbol or a number. Okay, so I see what you're doing. I think I wasn't clear about notations. So this letter Y, one single letter Y, represents the length of side BD. So Y represents distance from B to D. So you don't have to write Y and something else. It's either or usually. So it's either BD or Y. Now 10 represents the distance from D to A. It's a length of the side AD. So AD equals 10 feet. And I'm not sure. Can I do this? We can make it fit in here. So BE, distance from B to E equals 9 feet. And this distance, EZ, or EC, sorry, equals Z feet. So these are symbols. And BD is Y. So we just write the symbol that represents this side over DA, A over AD is 10, equals BD, which is 9, over EC, which is Z. So this is the better way to approach it. It makes further work for the algebra easier, less symbols. And less symbols means less probability to make a mistake. Now, this equation has two variables, two unknowns, so we cannot solve it. All we can say from this equation is the product of extremes, y times z. What's going on? Y times z is equal to, what is it going to be equal to?
10 times A.
This is 9.
Oh, 10 times 9.
10 times 9, and 10 times 9 is 90. So that's all we can say about this part. But we've got more lines and more triangles. So I have to go back to right here and then there. So to the theorem. Again, let's do this. So the theorem says, again, BD over DA equals BE over EC. This is our knowledge. However, based on the same strategy which was used to prove the theorem, we could prove other relationships. For example, BD over BA will be equal to BE over BC. So we should be able to visualize those segments, parts of triangles, parts of figures. So what I said now is this divided by this should be equal to this divided by this. And again, we should see the similarities. The sides, which we use in the numerator and the denominator, they kind of, again, across each other. Short across another short, long across another long. And this actually is not an easy, not a complicated exercise, because if we know this, step number one, and from picture, I can write that AD plus DB equals AB. Basically, that's what I'm doing. One side plus another short side gives me a long side, and I can write CE plus EB equals CB. Again, on the other side, this plus this equals that. So these two relationships together will give you, after certain algebraical manipulations, and the easiest, just cross multiply everything. Again, use the fact that extremes, the product of extremes equal to the product of means. You will prove this. But again, proving is just a good exercise. We don't have to do that every time, but being able to use it as a different thing. Another important relationship we can write for other sides. For example, this one and this one. DE over AC equals what? Well, we always should look at a part of a triangle, one or another side is what triangle does it belong to. So DE belongs to this small triangle. So I can use any other side from this triangle, for example, BD. But then AC belongs to a larger triangle. And in that larger triangle, there's a side similar to BD, but longer, BA. And this is another relationship, another ratio. And now, again, this is just an extra work which could be done again and again and again. We could establish another bigger triangle. So A, B, C, D, E, let's say F, G. And now for that extra triangle, we can write another similar relationships. So this single picture represents a lot of proportions, a lot. That is correct.
It is.
Yes. This is done by complete analogy, and it is absolutely right. But there is one more, which also is important, which connects shorter sides. dA over AF, for example, will be equal to EC over CG. These sides of course, these sides belong to different triangles, so there are similar relationships and some algebra, so done. But I believe after all these examples, we kind of see which sides related to which sides by proportion. There's some kind of symmetry in relationships. And now we can go back to any of these triangles, any, and just pick any sides we like on the left and on the right and relate them. For example, I can relate these two sides and these two sides by the relationship. Or I can relate this and this with this and this with this and with this. And if we move on to other pictures, it's exactly the same situation. The vertex, doesn't have to be at the top. It could have been at the bottom, on the left, and the right. It doesn't matter. We can see exactly the same situation. We can see a vertex. We can see two lines crossed by other, and we can see sides, for example, this and this. This and that in another triangle. So we can see a vertex and we can relate this. And well, I forgot, I think I did mention that. So you can see these symbols, they all are present. It means that these lines are parallel to each other. Of course, if that wouldn't be a case, the theorem wouldn't work. The proof of the theorem is based on the property of parallel lines. So these lines are parallel to each other. So I would suggest just practice at home, because there isn't much to add. There's a theorem, and there's a set of proportions you could write, and as long as you write several, you've got equations like this one, and you could do some algebra and just solve those equations, calculate value of all unknowns. Any questions?
How do I solve number? Like using the theory.
Let me see if I have. I need a bigger picture. Just a second. Now I need to share my screen. I'll do that. All right, I'm sharing my screen. So I hope you can see it. So again, let's take a look at the first situation. I'm going to be writing all possible proportions. So y over 9 equals 10 over x. Y over 9, 10 over x. Next one. 10 over 6 equals x over 8. 10 over 6 equals x over 8. And if you feel like you're not sure why, can I write it? Ask. If you're fine, fine. What I can see from this expression, I can see y times x equals 90. Doesn't help much. But what I can see from this expression, and this is always the strategy we have to apply when we are solving a problem. We write an expression. First step, write what you can. Second, simplify as much as you can. Third, ask yourself, can I use it? And so far, the answer is no. If the answer is no, next step is write another expression. Write something else. Of course, for that, you need to search and for additional relationship. And when you find it, write it like I did. This is my step number 5. And then again, the same question. Can I use it? So this expression, number 5, can we use it? Yes or no?
Yeah.
Yes, because in this expression, we've got only one unknown. So in this expression, I can simplify, and this is going to be basically 10 times 8 divided by 6. That gives me x. So check. However, now I have a new value, a new variable. I know something that was unknown. So now I ask a question, can I use this? And the answer is yes. Because now, if I know what x is equal to, I can use it here to calculate the y. And y will be equal to 90 over x, which is going to be 90 times 6 over 10 times 8. And this is a solution of this problem. But what is much more important, these steps, 1, 2, 3, 4, 5, 6, these steps tell you how to solve any similar problem. You just have to repeat the steps, repeat the strategy. So grasping the strategy is much more important than solving a specific problem. And again, right now we know what to do. I can write, for example, using these sides n over 2 will be equal to 6.5 over 5. And that's actually an easier situation. I can get n immediately. And here I can use exactly the same proportion. 2 over 3 equals k over 8. Again, simple. So this problem turns out to be the most complex out of all these problems. Any questions?
Why
Cannot hear you.
is y 9?
Y will be equal to 0, 6 times 9, 54 over 8. So you could reduce it by what? 54 is going to be 27 over 4. That's it. But if you take a calculator, you can convert it into a decimal. This is something I don't know if you're supposed to do or not. It depends on the teacher. Technically, this is the answer already because it's irreducible further, but 6.25 is the number you get if you divide 27 by 4. So this is a situation when, let's say, on the exam, unknown teacher, you should ask, what should be the format of your answer? If a fraction is fine, that's a regular fraction, or you want a decimal, or you want it in a regular format, I don't know. So
How do
okay,
you find the
go ahead.
how do you find letter Z here?
Oh. First of all, the question, how do we find, first should be answered in the most general form. If we have two lines crossed by parallel lines, it tells us we have to apply the triangle proportionality theorem. The triangle proportionality theorem says that you have to write a certain proportion. A proportion, well, technically, you should go to where is it? Well, you should go to your dictionary, to last pages of your note, and find what is a proportion. The proportion is an equality of two ratios. When a ratio is equal to another ratio, that's what we call proportion. So the answer to a question is, to find Z, you need to write a proportion which has a letter Z in it. That's your goal. That's your mental task goal. So you have to look at the picture and write ratio number 1, ratio number 2, which should be equal to each other. And one of these ratios should have a letter Z. That's your goal. So this is an answer to the question, how should we write a proportion with a z in it. So okay, you can try to write the proportion. So I would see it.
How do I do that?
You did it?
I had a paper on me for the actual sheet.
Ah, okay. So perfect.
I got y over 10 equal to 9 over x, but that's not gonna do. So I'm trying to think through.
Where is it? So you should apply the theorem to two triangles. Small triangle has y and 7, large triangle has other side. So this over this should be equal to this over this. That means y over 7 should be equal to y plus 10 over z.
I don't see what you're writing. I only see it again.
Yes, just a second. I need to share my screen again. Well, I'm gonna write it right here. So it's very small. Okay. It's very inconvenient. So much time is spent not on writing, but on switching between things. So now you can see it. Thank you for telling me. So this is the proportion I wrote. Why? Because we looked at this triangle, small triangle, and then large triangle. So there's a small triangle, there's a large triangle. In small triangle, we've got 1 and y and 7. And in the large triangle, we've got y plus 10 and z. See what I'm saying? And of course, because the value of y is known, 6.25, we can solve this for z. Let's do some algebra.
6.25 over 7 and over z. So it's gonna be 70 over 6.25 degrees.
Well, z will, so this is something I don't know, have you learned it or not? Properties of, again, proportions. For example, you can solve it for A, that's going to be B times C over D. And you can solve it for D, that will be equal to, well, we could do it in steps, for example. First, A times D, the product of extremes. Can you see it? Yes. I'm sharing the screen, you should be able to see it. So A times D equals B times C, and D will be equal to B times C over A. So this is something you've been doing, I saw it. And we could apply the same algebra to this geometry. Z will be equal to 7 times y plus 10 over y, which makes it 7 times, since y is equal to 6.25, it's going to be 16.25 divided by 6.25. And
Oh, I was close.
7 times 16.25. 18.2. 18.2. What is most important in this case is do not forget that when you use these triangles, you have to relate whole sides. So that's why on one side and one ratio you got y, and another has y plus 10. Y plus 10.
What did you do? 1 plus 10?
So this is the original situation, but this situation is equivalent to comparison of two similar triangle, small one versus large one. We just need to make sure that in these triangles are similar, which means all sides of triangles are parallel, corresponding sides, all angles inside the same. So, and again, the original statement was dB over dA equals BE over CE. Short sides, but based on additional amount of work, other ratios have been proved. And one of those is that we get these sides and calculate the ratios. We should get the same result. So dB over AB should be equal to DE over AC. But now, if we go back to the original picture, we could use different symbols. dB is Y, dE is Z, or else, where's the picture? Oh, 7, sorry. 7. And AD is 10 and AC is Z. So it is actually very helpful to write down, don't keep it in our mind, to write down what is the meaning of each variable. Y represents dB, 7 is DE, Z is AC, and if I write AB, what should I write for AB? I'm not writing ratios just yet. I'm just writing what every side is equal to as another symbol or a number.
Oh, 16.25.
Well, I don't have 16.25. I have 10 and I have y.
Oh, 10y. Or 10 plus 1.
Those are two hugely different things. 10y is 10 times y. Completely wrong. 10 plus y is correct. So this is why we get our ratio. So how do I do y over 10 plus y equals 7 over z. Well, and again, z will be equal to 7 times 10 plus y over y. Or in numbers, as we did it, 7 times 16.25 over 6.25. Okay. So I think the best way would be practicing of what you always can do is kind of pretend that we didn't do this and do these problems again at home as a homework on your own. And I believe probably you can find in your textbook more similar problems to just practice.
I have like a 4 here.
Any questions about these type of problems? I believe you need to do it as a homework again. Now, what I see next is several pages on similarities dilation. And again, everything begins from a definition. If you need to make a statement, if something is similar or not to another thing, you have to be able to say out loud, what does it mean to be similar? So it has to be a part of your dictionary, of your handbook, and you need to know how to compare, and then you need to know how to explain what you did. And similarity means angles are the same and ratios of sides. Yeah. So for yourself, you probably should have a shortened version of these statements. So corresponding angles are same. The ratio of corresponding sides is the same. And in this case, you should not just say yes or no, at least at home, but also show your reason for that. For example, if you say all right triangles are similar, you say no. The best way to prove this is actually to demonstrate an example when this statement is wrong. So you can just draw two right triangles, which will not be similar clearly. So they have identical side number one angle, but clearly other parts are different. Here, you should have been writing something like this. What is happening? So, oops. Based on a definition of similarity, if you need to prove that things are not similar, you have to show that the ratio of corresponding sides is not equal. So for example, again, mn over m prime n prime. That's going to be 2 over 1. We can see that. But if I use these sides, Lm over L prime m prime, this ratio is 1, well, 1 over 1. So because the ratios are not equal, the figures are not similar. If you don't show the reason, don't show the proof, that's not right. And yes, why? Well, technically, in this situation, you should write 4 ratios for this pair, and for this pair, and for this, and for this. And when you get 4 ratios, and they will be equal to the same number, which is, what is this? Which is 2. Yeah. Kg or k prime j prime equals, or you can see it. It's outside of your zone. The red line. I'm going to start sharing my screen. So these are figures, and that's going to be 2, because you've got 2 diagonals divided by 1 diagonal, etc., etc. For each pair of sides, you get 2, you get 2, you get 2, and then you say, because for each pair of corresponding sides, the ratio of the lengths is the same. That means, based on this definition, these 2 figures are similar. That's how it's supposed to work. And again, it is very, very helpful, very handy to have in one place a set of all rules about similarities, including rules about triangles. But I think here you made a mistake. If you look at these triangles, these 2 angles are equal because we are told, we are shown these angles are the same. The symbol, a little arc, tells us that the measure of this angle is equal to the measure of this angle. That's a given. However, we also see, how do we call these angles? What's the name for the angles like that, made by 2 crossing lines across each other?
Perpendicular?
No. These angles called vertical. And it tells me that you have to learn the vocabulary. Because if in the future you will read this term, vertical angles, you will not know what it means. So this is why vocabulary is crucial. Vocabulary. Do I have more? No. So, and again, you go through a textbook and you see a blue box usually, and it says sometimes definition, and it says, for example, two angles made by two crossing lines opposite each other called vertical. So you have to go to your notebook and copy this definition. So you have to build on your own handbook. Because in this situation, terminology is crucial. So on vertical angles that are equal. So you've got two triangles with two equal angles, which means these triangles should be similar. Now, when you talk about similarities, it's very important to know, of course, all operations which could be used, transformations, and you know those, I can see that. But sometimes it's very important to actually read word by word. What do we need to answer? In the last part, I'm going to read it, and that's going to be my last example for today. It says, one definition of similar triangles is based on transformations. So similarity is based on transformations. However, there are other criteria. What are those criteria? And you answering reflection, dilation, rotation. But those are transformations. So you've been asked about other criteria different from transformations, which means saying existing transformations does not answer the question. So what are other criteria? Well, that should be a part of our knowledge. Other criteria are these. Where is it? Here, triangle similarity. Angles, sides, size and angle. So here, your answer should have been AA, SSS, SAS. So this is something which comes with practice. When you read a statement of a problem or a question, it's very important to analyze every word, basically. Well, any questions? So I've got more slides prepared, but we have to find another time for those, unless you will send me an email and you will tell me that, okay, I don't need this anymore, let's talk about something else. So here we got proportions, and the last part is about triangles, right triangles. So I think we should talk about it because I don't see a work, so probably I should explain this and then we should practice. But again, this is up to you. Any questions for now? All right. So I'm gonna send the slides to you. And please feel free to send me an email with any follow-up questions or suggestions on new material or anything else. And think when, if you would like to have another meeting, and just let me know, okay? All right. Well, have a nice day. Bye.
Bye-bye.
Okay.